Swayam Prabha. Digital India. Educated India.
Non-recursive phrases. That means phrases which do not contain other phrases within themselves. So things like the blue sky, but not the blue sky which is far, far above. Okay, so those kind of phrases are in the realm of deep parsing. We're interested in shallow parsing. And we'll take base phrase, non-recursive phrase. And our instrument or the technique will be conditional random field. There is a very celebrated paper for this, Lafferty, McCollum and Pereira. It was in ICML 2001. Conditional random field is an example of graphical models. Okay, and you will see that whatever you understood in hidden Markov model is directly translatable to conditional random field also. Only thing is that we will not apply Bayes theorem for conditional random field and get two different parameters of transition probability and emission probability. We will work with only conditional probability, and that is still better. Okay, for running Viterbi algorithm, just working with conditional probability is much better, more convenient, because we do not have to worry about the product of two probability terms. Okay, so we'll see the modeling, how the technique is applied. And we need tremendous support from morphology because conditional random field will work with features, okay, on the text. Now, many of you have asked the question of how to deal with unknown words, which is also the data sparsity problem. Now, mark my word at this point of time. Mark my word. Sparsity problem can only be solved by going lower, going backward in the NLP stack. That means if you want to solve the data sparsity problem for part of speech tagging, you will have to appeal to morphology. That's a must. Okay, so if a word is seen in the test corpus, which is not in the training corpus, you have not seen that word before, then you have to look inside the word. Okay, you have to look inside the word. You have to break the word apart. You have to work with the property of the word. So I'll add a slide on this because I'm saying this impromptu based on my experience of dealing with language, that solving of data sparsity in NLP is done by going one step back or two steps back, going lower down the stack. Let me illustrate. If you do not know what is proposition as a word, proposition, okay, you have not seen it in the training data. Now in the test sentence you have encountered proposition. What is the part of speech tag of proposition? Well, I look into the anatomy of the word. I break the word into two parts. It is propose, proposee, and tion, shun. And from my training data, I have seen that the shun words are nouns. Okay, so proposition also would be noun, is my decision. So, and their decision is correct. Okay. Now, what did I do? I broke the word proposition into two parts, proposee and shun. That is a morphological process. Okay, that's a morphological process. And sometimes we are also required to look at the property of the word. What do I mean by the property of the word? Length of the word, for example. Okay, length of the word. So Suppose I have not seen the word oh. Oh, the sky is so beautiful. So this word oh did not appear in the training corpus. Now I see that the word oh has length of 2. And normally the interjection words, the exclamation words, are 2 letters long normally. So I'll take a risk and say that O is a interjection. And I'll be okay, I'll be correct here. Okay, I'll be wrong many times also, but I'll be correct here. This is better than maybe saying nothing about O because it was not seen in the training corpus. So I hope you are appreciating this point, that to solve data sparsity, you have to break the word apart, looking at its parts, or you have to take the properties of the words like length, the number of syllables, if you have that kind of instrument, and so on. So word parts, word properties. Do remember this. I'll add a slide there. Word parts and word properties. So for those of you who are asking this question of how do I deal with unseen words in the training data, my answer would be there is only one way. You have to deal with the word parts and word properties. Okay, there is no other way, and there are techniques to exploit this idea through different kinds of smoothing, where I have sent you a reference. Not everything will be possible to be discussed in the class. You will have to do your own reading also quite a lot, and I'll keep sending you pointers to reading material. So the agenda is conditional random field and chunking, support from morphology, and evaluation of pause tagging, which is a general concern in your mind now because you are making some progress with the assignment, namely part of speech tagging. So let me take the last agenda first. Evaluation of sequences when they are labeled. Okay, sequence to sequence labeling task, and we would like to evaluate the accuracy of sequence labeling. Part of speech tagging is something we are familiar with. You are also working on part of speech tagging. We have a very simple part of speech tagging situation, and I think with the universal pause tagging repository, you are also in a rather simple situation of dealing with only about 15 tags when you're working on the assignment. And as I've said many times, take your assignments very seriously. NLP cannot be learned only by reading and listening to lectures. You have to burn your fingers with actual text corpus. So we have only 6 tags here. Determiner, noun, verb, adjective, adverb, and others. They are shown against each word. And there is a sentence beginner in the form of hat, sentence finisher in the form of dot. And by now you must have understood very well that our task is to find the best path from hat to dot, traversing the states of part of speech tags. The transition from one state to another is in the form of the product of transition probability and the emission probability. So if you have a probabilistic finite state automaton with marked start state and marked end state, then you have a technique for finding the best possible path efficiently through the Viterbi algorithm. So independent of what algorithm you're using, hidden Markov model or conditional random field or maximum entropy Markov model, there is one definite point that if you have a graph where state to state probability, which can be product of transition and emission or simply conditional probability, you can find the best possible path from start to end. And from start node, you will go to as many children node as possible. And then from there, grandchildren node and so on. Then you can find the path efficiently. So that technique we have seen already. So this is how the search tree develops, and Viterbi algorithm gives me a way of finding the best possible path efficiently. Now question is, how do we evaluate? Well, if I take this sentence, the black dog barks, I find that the tag for hat is hat, the tag for the is dt, the tag for black is noun, the tag for dog is VB, and barks also is VB, dot is dot. So there are two mistakes in this tag sequence. Black is not noun, it is JJ, adjective. Dog in this case is not a verb, though dog can be a verb. Dog in this case is not a verb, it is a noun, the black dog. So 4 out of 6 tags are correct. So precision, which is nothing but number of correct things out of all the things, is 4 out of 6, which is 66.67%. All right. So this is the first measure of evaluation, which is precision. There are two others, recall and F-score. Recall and F-score, which I can mention later, or it is also easy for you to look up what is recall. Precision is how many are correct out of everything obtained. Now, my precision from this sentence is 66.67%. Can I claim that this will be true for the whole population? That means, can I ask the pause tagger that I have built, will it for all time to come function with 66.67% precision? That means, will it on an average tag 67% of the words correctly? That means, on an average, if I have a 30-word sentence, 20 times 20 out of those 30 words will be tagged correctly on an average for all time to come. Can I say that? Not really. Intuitively, you can say not really, because your claim is based on only one sentence which has been tagged. So this points to the fact that we have to take many sentences and tag them and then compute this kind of precision value. So this intuition is given a formal framework through probability. Now the precision question is very similar to the coin tossing problem. For every word I ask, is it correct or not? Is the tag correct or not? So it's a binary decision, correct or not? Very similar to coin tossing situation. If I have n tosses of the coin, is it head or not? That is it success or not? Success means head. So here precision is k by n, which is nothing but the parameter of the random experiment. The parameter is the probability of head, k by n, very similar to the precision question. So now we are in the realm of what is called Bernoulli trial and binomial distribution. The probability of k successes out of n trials with parameter p is given by this binomial expression nck p to the power k 1 minus p to the power n minus k. However, the discrete probability distributions do not give us very naturally a method of saying something with confidence, where confidence is a technical term here. It doesn't give me a method of placing my results in a confidence interval. Here I'm becoming a little more technical, and we'll have occasion to talk about this when we do test of hypothesis. But binomial distribution can be approximated by normal distribution. When n, the number of trials, is large and the probability of head p is close to half, then this is approximated by a normal distribution whose mean is np and standard deviation is npq, q being 1 minus p. And the moment you are in the realm of normal distribution, you have a huge machinery of theorems, lemma, etc., by which you can say, make a statement with confidence. Typically, the confidence interval is 95%. That means you have the possibility of error of 5% only. So all these instruments can be used, and I can claim with 95% confidence that my part of speech tagger has an accuracy of, let's say, 80%, 85%, and so on. All this theory can be very cleanly and systematically and elegantly built using the properties of normal distribution. I am giving a series of lectures on application of probability to AI. So where I am discussing those points, which is in a different lecture. So the way to calculate precision, I think you have understood. Recall is how many we could capture out of the actual space, okay, abstractly speaking. So in recall, part of speech tagging, the recall question is how many tags are obtained from the correct repository of tags, from the repository of the actual tags. Now, if you're tagging every word, it turns out that precision and recall are same. Therefore, F score is also same. I have not defined them, precision, recall, F score. We'll have an occasion to define this maybe next class itself very clearly. But if you're tagging every word in a sentence, precision, recall, and F score will be same. Now, I'd like to go into morphology purely from the support point of view. Morphology supporting part of speech tagging supporting shallow parsing supporting deep parsing supporting semantics supporting pragmatics, and so on. So there's the whole stack of NLP which has this dependence backward. Okay, and you'll be interested in knowing that there is dependency forward also. That means many problems, ambiguity problems, are solved by back and forth information transfer, for which deep neural network is an appropriate framework. Okay, so this we have remarked in the beginning. Now this morphology discussion, I would like to acknowledge the presentation by Mugdha Bapat, one of your seniors, an MTech student in our CFIELD lab in the CSA department, and it is based on discussion in a very classic linguistics book from MIT Press by 4 authors. The first author is Akmajian. The book name is Linguistics: An Introduction to Language and Communication. So 7th edition means you can appreciate that point, how relevant the book has remained over time. It is not common to get a situation where a book is printed for its 7th edition. Shakespeare, Bible, Gita, these are printed many times over. They have nth edition where n is very large. But for a textbook, 7th edition is great. Now, what is morphology? one of that, somebody from the TA team verify this is the screen. What is morphology?
Yep, this is it, sir.
Okay, and somebody from the student team, please verify this. What is morphology? Okay, great. Okay, so morphology, very simply put, is the study of words, and you break the word. That's all. You break the word systematically. So washing is wash plus ing, and ing is very productive. You can have productive means the same process repeats for many entities. That's called productivity. So washing is wash plus ing, walking is walk plus ing, going is go plus ing. So this is a very productive process, and morphological processes are normally quite productive. Same uniform process applies on many large number of words, and this happens across languages. Okay, not to say that only English has this productive process. Marathi has, Telugu, Tamil has, Italian has, all languages have. And in fact, it is seen that the older the language, okay, this we're saying something from the perspective of historical linguistics. There is something called historical linguistics. Older words like Latin, Sanskrit, Greek, Hebrew, Arabic, these languages have very productive process in morphology. Okay, one uniform process applies on so many different words, and that is also a sign of rich morphology. But modern languages, let's say I can say Bengali, Assamese, these are modern languages. Tamil is a very old language. Modern languages tend to simplify morphology. Okay, they tend to simplify morphology. They tend to have less number of things to do in morphological processes. So, and depending on that, a language falls in a spectrum: rich morphology versus weak morphology, let's say. So English is not a very strong morphologically rich language, whereas Marathi is much richer. It is richer than Hindi in terms of morphology. So what is the proof that Hindi is richer than English and Marathi is richer than Hindi? What is the proof? The proof is in the fact that for different situations, you have different manifestations of the word form. So if I say going, okay, will be going, then it is not clear, is it first person, third person, or second person? I will be going, you will be going, he will be going. See, everywhere the will be going form is same. You need additional information to know, is it first person, second person, or third person? But not so in case of Hindi. Jaunga immediately shows first person, I am going. Jaoge immediately shows you are going. Jayega shows he is going. Okay, so for different situations, different word forms, that is a sign of rich morphology. And productive processes mean that this process of different word forms for different situation will apply for large number of words. Okay, so similarly we have plural formation. Bad becomes bads, write becomes writer, browse becomes browser, rat become rats, and so on. So this is also a productive process. Pluralization is a productive process. And morphology tries to formulate the rules that show the knowledge of the speakers of those languages. Now, morpheme is the smallest linguistic piece with a grammatical function. So if I have the word reconsideration, then re is morpheme 1, morpheme 2 is Asian, and consider is the base morpheme or stem. So re means repeat, and Asian converts a verb to a noun. So very definite grammatical functionality. Okay, so re is a semantic property of the word, indicates repetition, and Asian is a grammatical property which changes the part of speech of the word, reconsideration. Then all these complexity of morphology analysis, this undertaking this task of breaking a word into its parts, looking inside the word, dealing with its properties, all this, is it worth doing? Okay, so for that there are numerous studies, and we have also shown this from our lab in 2010 through the work of Mugdha Bapat, Harshada Gune, and Mitesh Khapra, three of my students at the time.